We propose neural part priors, which are learned parametric object part priors encoded into latent spaces that can be optimized over at inference time, fitting precisely to objects in real-world scan scenes and enabling accurate, holistic scene reconstruction. Our aim is to parse real-world scene observations into their part decompositions via test time optimization over a parametric part space, enabling accurate geometric representation of input observations and ensuring part consistency between similar objects detected in a scene. Current methods make independent predictions per object, with a single forward pass on each detected object. This produces both inconsistent predictions in a scene, as well as results that do not precisely match the input geometric observations. Our approach takes as input an RGB-D scan. We first estimate independent predictions for part decompositions of each detected object. We then refine the estimates by optimizing over our parametric latent space to fit both input geometry constraints, as well as inter-object constraints for holistic reconstruction of similar shapes. We operate on voxelized input scan data and use detected object bounding boxes from a state-of-the-art 3D object detector, MLCVNet. For each detected box, we estimate its part decomposition into a set of part labels and an initial latent code in our parametric part space, along with a proxy shape code to represent the complete shape geometry. We also simultaneously estimate the part segmentation of the detected object. We can then use the predicted latent codes to initialize test time optimization to better fit to the observed input geometry, taking into account part shape consistency and intershape consistency within a scene. To build our neural part priors, we learn comprehensive part and shape latent spaces from synthetic partnet data, based on autodecoder training to reconstruct part and shape geometry. Then, for each detected object in an input scan, we extract features by a convolutional encoder to predict the object's shape feature representation, from which we estimate the object's semantic part structure as a set of part labels and corresponding part features. For example, this chair is decomposed into its chair legs, seat, and back. We predict up to a maximum of 10 parts per object, along with their probability of existence. The predicted part and shape features are then projected by a small MLP into our pre-trained part and shape manifolds, which can then be decoded into implicit SDF geometry. Simultaneously, we estimate part segmentation from the input TSDF and the predicted shape feature, producing dense part segmentation, including for background regions. We use the initial part and shape code estimates to initialize optimization over our parametric part space to better fit to the input geometry. We backpropagate through both decoders using the estimated segmentation to traverse over the latent spaces. We take into account the reconstruction consistency between parts and shape to ensure a coherent part decomposition. Furthermore, if there are similar detected objects in estimated shape geometry, we aggregate constraints from all such objects to produce a consistent, accurate reconstruction over the whole scene. Here we visualize the optimization process. Our learned part and shape manifolds are able to provide rich spaces, yielding smooth interpolations. Our learned part space enables more accurate reconstruction, outperforming state-of-the-art in chamfer distance for complete part decompositions of scenes. This similarly enables improvement over the state-of-the-art for part segmentation, which does not consider any completion and evaluates only the observed geometry. We show qualitative results of semantic part completion on the ScanNet dataset compared to alternative methods. Our optimizable parametric prior-based approach produces more consistent geometric part structures, resulting in holistic scene reconstruction. Thanks for watching.